Hey guys, in this video we're going to be talking about VSEPR or valence shell electron pair repulsion theory. In this video we're going to be looking at how VSEPR works, what electron groups are, and what positions atoms end up in when we're in different geometries. We're going to know at the end of this what an electron group is, an electron domain, and use it to determine our electron domain geometry and our molecular geometry, and then predict 3D molecular shapes and determine bond angles, all from this same thing. So let's start looking at Lewis structures. To do a VSEPR structure, we have to know the Lewis structure first. So it's important to understand how to do a Lewis structure, first of all, and second, the way that you characterize the things around a Lewis structure. So when we look at a Lewis structure, we have central atoms, we have terminal or peripheral atoms, and then we have bonds and lone pairs. So there's lots of different things within a Lewis structure. So a Lewis structure itself gives structural information that can be used in VSEPR to determine three-dimensional structure of the molecule, including bond angles. Okay, so the Lewis structure itself doesn't give us information about the overall shape. It's our VSEPR that will give us overall shape. We just use our Lewis structure and VSEPR to get together our three-dimensional shape. The components of a Lewis structure include bonds, lone pair electrons, central atoms, and peripheral or terminal atoms. Okay. So from our Lewis structure, we can find out what things are bonded to what and where the electrons are. But in order to get to a molecular shape and bond angles, we need to look at more information. Okay, so Lewis structures are often misleading in the way they are drawn. For instance, if we look at carbon tetrachloride over here, from the Lewis structure itself, it looks like we have 90-degree angles, right? However, that's not true. So the bond angles are usually not represented within a Lewis structure, which is why we need another theory in order to determine the bond angles. And our 3D shape. Keep in mind when we're drawing things like a Lewis structure, you're drawing on a piece of paper, but if we're talking about a molecular shape, we're talking about something that is in 3 dimensions. So it has the ability to be in the X, Y, and Z planes. It's not just confined to X and Y. Okay, so when we are doing our molecular shapes and bond angles, we're going to look at what's called the formula of a molecule. So looking at what things are around our central atom. Okay, so formula takes on the structure A, B, N. So A is our central atom, and then B is our peripheral atoms, and there are N of them. Okay. And the first different geometries we're going to be looking at, we're going to assume that there are no lone pairs around our central atom. So let's look at some ABN geometries where A doesn't have any lone pair electrons. Okay. So here are our different ABN geometries, assuming all of these are atoms instead of electron pairs. So we start out with an ABN geometry where n is equal to 2. And here in our n equals 2, we are going to have a linear geometry where all three atoms are in a line. Hence the linear. Next, we have n equals 3. This is called a trigonal planar geometry. And here, the atoms make a triangle around the central atom. So this one right here. Okay. So we can see this triangle right here. And we have 120-degree bond angles. Okay, the linear one had 180-degree bond angles. Okay, next is our n equals 4. N equals 4 looks like a tetrahedron, so it's called tetrahedral. And this is the first geometry where we're not just in one plane, right? So the linear geometry and the trigonal planar are in one plane. Our tetrahedral brings us into our next plane, and we have 109.5-degree bond angles. Next, we have n equals 5. This one right here. And here we have what's called trigonal bipyramidal. And it's called that because we have a triangle, and on top of that triangle, we have a pyramid. All right, so we've got a triangle based pyramid, and there are two of them. So, two pyramids with triangle bases. Okay, and this has 90-degree angles and 120-degree angles, as we see there. Okay, and then n equals 6. This is called octahedral, and it's because it makes an octahedron, which is a 8-sided shape. Okay, and here all our bond angles are 90 degrees. Okay, so let's just real quick zoom in on these so we can get a better look at them. I'm just gonna erase. There we go. So we've got our 2, 3, 4, 5, and 6. For 1, we've got our central atom right here and our 2 peripheral atoms. Next one, we've got our central atom, 3 peripheral atoms, and the furthest we can get them away from each other is 120 degrees. And then we have our central atom surrounded by 4 peripheral atoms. And here, each of our bond angles are 109.5. And our central atom with 5 things. And we have, this is the only one where we have 2 different sites. We have the site right around this central equator. And then we have 2 sites above and below that central equator on the axis. Next is our octahedral, where we've got 6 atoms around a center point. So it's called octahedral, not because of the 6, it's because of the shape itself. We have an 8-sided shape. On each side, we have 1, 2, 3, 4 sides on the top, 4 sides on the bottom. Okay. Next, let's look at what happens when we take one of those atoms and replace it with a lone pair of electrons. So we can take what's called the derived molecular shapes. So these are made by replacing one or more peripheral atoms with lone pairs. For instance, let's think about the tetrahedral shape. So we have a central atom that has 4 peripheral atoms around it. And we're going to remove one of these and replace it with a lone pair. These are still approximately 109.5 degree angles because we still have repulsion coming from this electron pair right here, but it's still a little bit different. We'll talk about that in a little bit. And now we place one more with an electron pair, and we get a structure like this, and again, approximately 109.5 degree bond angles. When we look at the shape that all of the electron containing things have, that includes bonds or our lone pair electrons, the shape looks exactly the same. It still looks like a tetrahedral. But when we think about what the atom shape, the shape the atoms themselves make, right, it's going to look a little different. So this is our tetrahedral geometry right here, right? So we have our little tetrahedron. And then we look at this structure. it looks a little different, right? Looks different from what the initial thing looked like. And then if we look at this one, it looks different as well. So what happens is we go from having a tetrahedral geometry of our atoms to a trigonal pyramidal geometry to a bent geometry. And this is just considering at the atoms. Okay? So what shapes the atoms make? And this all brings us into what's called valence shell electron pair repulsion theory, where our electron pairs are going to arrange themselves around a central point, our central atom, in such a way as to minimize repulsion. So, electron pairs, or electron-containing entities, such as bonds and lone pairs, will repel other electron-containing entities. Vesper describes the shape of the resultant molecule which places electron pairs around a central point as far away from each other as possible. To minimize repulsion. Okay? So you're just basically taking anything that has electrons, bonds, or lone pairs, getting them as far away from each other as possible. There are two types of electron domains or electron-containing entities. And these are going to be bonding pairs and non-bonding pairs. Or bonding electrons and non-bonding electrons. Bonding electrons is going to be electrons that are in bonds. And our non-bonding are electrons not involved in bonding. So our bonding electrons are going to be between two nuclei. And our non-bonding will be attached to only one atom. Okay, but both of these, both are considered electron domains. Okay. Another thing to note about bonding electrons, so these are our bonds themselves. And they could be single bonds, double bonds, or triple bonds. Okay. So let's look at our electron domain geometries. So the electron domain geometries, these are geometries that are based on the initial ABN geometries. Okay. So as a note, the geometries will be the same whether B is a bonded atom or lone pair. Okay. We also have something called the molecular geometry. And these are based on the derived ABN geometries. Okay. So the shape depends on amount of bonded atoms and lone pairs. So with our electron domain geometry, we don't really differentiate between the two of them. We do a little bit when we're looking at our bond angle, but in general, an electron domain is an electron domain. It doesn't matter if it's a bond or an electron pair, a lone pair electron. With our molecular geometry, we're going to differentiate the geometries based on what type of electron domains are around that central atom. They're still going to have the same overall geometry of the electron pairs, but they're going to be described as different geometries based on whether we're looking at our electron domain geometry or our molecular geometry. So here are our electron domain geometries for our non-expanded octets. So if we zoom in here, they are the same thing we looked at earlier, but our electron domains can be bonds or electron pairs. So we have 2, 3, or 4 electron domains. If we have 2 electron domains, the furthest we can get them away from each other is 180 degrees. So the electron domain geometry is going to be called linear, and the predicted bond angles will be 180 degrees. That doesn't necessarily mean that's going to be the actual bond angles, but that's a predicted bond angle. Then if we have 3 electron domains around a central point, the furthest we can get them away from each other is 120 degrees, which gives us our trigonal planar electron domain geometry, and again, predicted or ideal bond angles of 120. Next is 4 electron domains. Furthest we can get them away from each other is 109.5 degrees, and that forms our tetrahedral electron domain geometry, where we have predicted bond angles or ideal bond angles of 109.5. Our electron domain geometries, they're geometries that are going to be based on just our electron domains. Doesn't matter what type of electron domain it is, whether it's a lone pair of electrons or if it's an actual bond. But with our molecular geometries, we're just looking at the geometry of the atoms within the molecule. It will maintain roughly the same bond angles as the electron domain geometry that it's derived from. But it's going to have different names to describe just what the atoms within the molecule looks like. And it's going to also be based on the central atom. So based on the geometry around the central atom, but just looking at the atoms. So let's look at our molecular geometries. So let's zoom in right here. So we can, with our linear, we really only have one option. It's always going to be linear. Even, if you have a bond angle, so to have a bond angle, you have to have 3 points, a central point, and 2 points around it. So you have to have 3 atoms connecting in order to have a bond angle at all. So with Vesper, you have to have those 2 bonding domains. So you won't have a non-bonding domain in linear, so it's still going to be 180 degrees right here. If we were talking about trigonal planar can either have 3 bonding domains, no non-bonding domains, and it'll have the same exact molecular geometry as the electron domain geometry because all the electron domains are atoms. So these have 120-degree angles, and we call it a trigonal planar molecular geometry and a trigonal planar electron domain geometry. If we replace one of those bonding domains with a non-bonding domain, so we put an electron pair in there, now we're just looking at the molecule in terms of the atoms that make it up, and we're kind of ignoring that lone pair. It's still affecting the bond angle, but now it's kind of taking up space and not really being, but still not being kind of observed. So when we have one non-bonding domain in a trigonal planar geometry, we get a bent structure. Now, with this, and I'll talk about this in just a little bit why, but this repels more than non-bonding. Than bonding electrons. So this angle is actually going to be less than 120 degrees. This bond angle is actually going to be less than 120 degrees. We can also look at our tetrahedral electron domain geometry, and if we keep all of our electron domains bonding domains and we have no non-bonding domains, we will have a tetrahedral molecular geometry. And then if we have 3 bonding, 1 non-bonding, so one of those atoms is replaced with a lone pair of electrons, then again, we're just looking at the structure that's made by our atoms themselves. And what we find is we get what's called a trigonal pyramidal structure, and it's because it makes this triangle base up to a pyramid shape, where that's our central atom, and then those are our 3 peripheral atoms. Then 2 and 2, we get the same structure we saw before, where we have a bent structure because we are ignoring these lone pairs. Now, in terms of bond angles, we have a 109.5 degree angle when our molecular geometry is equal to our electron pair domain geometry in tetrahedral. In our trigonal pyramidal, we get a 107. So that bond angle decreases because this repels more. And now, having 2, even more repulsion. And we get a bond angle of 104.5 degrees. So it basically decreases by 2.5 degrees every electron pair you add in a tetrahedral molecular geometry. So let's look at our steps for determining the shape of a molecule or ion. So the first step is always going to be determine your Lewis structure. You need to know what electron domains are there, how many there are, what types there are. After you've determined that, you're going to need to know which ones are non-bonding and which ones are atoms, and you're going to count them. So you're going to determine your electron domain geometry by taking however many electron domains you have and arranging them as far away from each other as possible to minimize that electron repulsion. And then this will give us our electron domain geometry. Then we can determine the molecular geometry looking at just the arrangement of the bonded atoms. And we're going to lastly evaluate our bond angles based on our electron domain geometry and taking into account the fact that lone pair electrons are going to repel more than atoms. So, take our structure, we form our Lewis structure, we determine our electron domain geometry by counting our electron domains. Then looking at our bonding versus non-bonding electron domains, we can determine our molecular geometry. So let's start by looking at a couple of examples. So step one, we start with our Lewis structure. So I've already got the Lewis structures for all of these drawn in. So that is always going to be your step one. Next, we're going to determine the geometry around the central atom by counting our electron domains. So in all three of these cases, we have 2 electron domains around the central atom. In this next row, we have 3 electron domains. I'm just going to do ED. And then last row, we have 4 electron domains. In the case of our 2 electron domains, we're going to have a linear electron domain geometry. In the case of 3 electron domains, we're going to have a trigonal planar electron domain geometry. And then in the case of 4 electron domains, this is going to be a tetrahedral electron domain geometry. Next, we're going to look at just the shape that atoms themselves are making, ignoring our lone pairs. Again, our lone pairs are still causing the bonds to have a specific bond angle, but we're just kind of ignoring them when we're thinking about what shape it's making. So in the first one, each one of these have a linear shape of the atoms. They're all in one line, so we have a linear molecular geometry. For the next one, we have 2 that have 3 bonding domains and 0 non-bonding. So if you have no non-bonding, your molecular geometry is going to be the same as your electron domain geometry. So both of these are trigonal planar. In the case of our germanium dichloride, we have 1 lone pair, so we have 2 bonding domains. And we have 1 non-bonding domain, which means we are going to have a molecular geometry that is different from our electron domain geometry, and in this case, it is a bent structure, giving us that less than 120-degree angle. Next 3 ones, we have 4 bonding domains, 0 non-bonding domains. So this is going to have a molecular geometry and electron domain geometry the same, which is tetrahedral. Our next one, we have 3 bonding domains and 1 non-bonding domain. So we get a trigonal pyramidal structure. And then last one, 2 bonding domains, 2 non-bonding domains. We get our bent structure. Okay, last step is going to be to evaluate the bond angles. When we have our linear geometry, all of our linear structures will have 180-degree bond angles. We go to our trigonal planar. We're going to have 120-degree bond angle, 120-degree bond angles, as long as all of our electron domains are going to be bonding domains. This one right here has a non-bonding domain, so this is going to be less than 120 degrees. And then we have our tetrahedral at 109.5 for 0 non-bonding domains, 107 for 1 non-bonding domain, and 104.5 for 2 non-bonding domains. We also, this one right here, because of this double bond, it's also going to repel more. So this bond angle is going to be less than 120 degrees. We'll talk about that in just a minute. So let's look at our electron domain geometry and molecular geometry of Cl2CO. So let's take this structure and get our Lewis structure. So we have 2 chlorines. Each chlorine has 7 electrons. That gives us 14 electrons. Carbon has 4 electrons. There's only 1. So it gives us 4. And then oxygen is 6 electrons and only 1. So 6, giving us a total of 24 electrons to go around our structure. Our carbon will be our central atom. It's the least electronegative. And then we're going to write our oxygen and chlorines around here, and that accounts for 6 electrons, giving us 18 remaining electrons. We'll put them around our peripheral atoms first. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That's all of those electrons taken care of. Next, we evaluate to see, is this a good structure? And hopefully we notice that, no, it's not quite a good structure because the carbon is lacking an octet. So we're going to take one of these lone pairs and place it in a bonding site instead of a non-bonding site. Now we have 8 electrons around each of our atoms. This is a good structure. Okay, now that we have our Lewis structure, we can evaluate our structure itself and figure out what our electron domain geometry and our molecular geometry and bond angles are. So if we look, we have 3 bonding domains. So we have, this is a bonding domain, this is a bonding domain, and this is a bonding domain. We have 0 non-bonding domains. Keep in mind, we're just looking at the bonding domains around the central atom. And this gives us a total of 3 electron domains. So 3 electron domains means we have a trigonal planar electron domain geometry. And because each of the electron domains are bonding domains, we also have a trigonal planar molecular geometry. In trigonal planar, our ideal bond angles are 120, but because of this double bond here, we have greater electron density right there that's going to push down, and this is going to cause this bond angle to be less than 120 degrees. Okay, so let's look a little bit more at our non-bonding electrons and why they cause more repulsion. So I told you with those non-bonding domains, you're going to have pushing down on the electrons around them, and that's going to cause us to have bond angles that are less than ideal the more non-bonding electrons you have, and it's because of effective nuclear charge. Okay, so if we think about a pair of bonding electrons, it's going to be surrounded by 2 nuclei. Okay, and as such, it's going to experience a certain amount of effective nuclear charge. So feels nuclear charge from 2 nuclei. Okay, and that's going to minimize the size. Remember, anytime we have a greater effective nuclear charge, we have a smaller electron cloud. Now, if we're talking about just one nucleus being attached to that electron pair, so non-bonding electrons, we only have one nuclei, which leads to significantly reduced effective nuclear charge. That's going to spread out and repel more. So they have a more repulsive nature, Then our bonding pair. So they're going to push down on those bonding pairs because they spread out more. So that's going to cause a decrease in our bond angle in tetrahedral from 109.5 to 107 to 104.5. We see a similar effect when we have multiple bonds, but here now it's just amount of electrons, right? More electrons, they're just going to repel more. And hopefully makes absolute sense that our triple bond is going to be the most repulsive out of all of our multiple bonds. So a triple bond, which contains 3 pairs of electrons, repels more than a double bond, which repels more than a single bond. But still the most repulsive is going to be our lone pair, and that's because it still has a smaller effective nuclear charge because there is only one nucleus. And we can kind of think about it a little bit like these additional electrons that are making up the double and triple bonds are going to be valence electrons, so they're not going to shield the nuclear charge as much. So our triple bond is larger because of the greater amount of electrons, but we still have a greatest amount of space and repulsion from our lone pair. Okay, let's look at our expanded octets. So with our expanded octets, we have 2 options. We can have 5 electron domains, or we can have 6 electron domains. With our 5 electron domains, we have a trigonal bipyramidal electron domain geometry, and 6 electron domains, we have an octahedral electron domain geometry. And for our bond angles, they both are going to contain a 90-degree bond angle, but our trigonal bipyramidal will also have a 120-degree bond angle. So let's look a little bit more at that structure. With a trigonal bipyramidal structure, we're going to have what are called axial positions and equatorial positions. Our equatorial positions are our 3 positions on the equator, and then our axial positions are the 2 positions on the z-axis. Okay, so we have 3 equatorial positions, and these are going to be a equilateral triangle around the equator of the central atom. And then we have 2 axial positions. And this is along the z-axis. Okay, so our 3 equatorial positions are going to be 120 degrees from each other. And then our axial positions are going to be 180 degrees from each other. And then our equatorial versus axial are 90 degrees from each other. Okay, so what happens is anything that is on an axial position is going to feel more repulsion than something on an equatorial position. Reason being, each of our axial positions, let me clean this up a little bit. Each of our axial positions is 90 degrees away from 3 equatorial positions. while our equatorial positions are only 90 degrees away from 2 axial positions. So axial positions experience greater repulsion. Because of this, electron pairs always go to equatorial positions. So you'll never have an axial position that has electron pairs, so always go to the equatorial positions. So let's look at these right here. So here are our trigonal bipyramidal structures. So we can either have 5 electron domains, 0 non-bonding, 4, 1, 3, 2, 2, 3. So at 3 bonding, 0 non-bonding, we're going to have our electron domain geometry and molecular geometry being the same at trigonal bipyramidal. When we replace one of those atoms with a lone pair, that is going to go in an equatorial position, and we get what's called a seesaw or sawhorse structure. Okay, so it kind of has, when we think about it, like a little that type of structure right there. So it looks kind of like a sawhorse, or if you flip it around, a seesaw. Okay, and then when we have 3 bonding, 2 non-bonding, now we get what's called a T-shaped because it literally looks like a T. And again, the second non-bonding pair of electrons is going to go in an equatorial position. And then lastly, our third non-bonding pair of electrons is going to go on the equatorial position, and we get a linear structure. Okay. Keep in mind that this lone pair of electrons is going to cause more repulsion, so it's going to decrease our bond angles. So just understand that as you increase your non-bonding electrons, it's going to cause more repulsion, and it's going to decrease the bond angles around it. And then our octahedral, it doesn't have anything special until we start increasing our number of non-bonding. So let's look at that. So 6 and 0, octahedral for our electron domain geometry, octahedral for our molecular geometry. We replace it with 5 to 1. We get what's called a square pyramidal structure. So what we get is this square base, and it makes a pyramid shape with our peripheral atoms, and our central atom is going to be in the center of that. If we take and we replace another atom with a pair of electrons, we are going to get what's called a square planar structure. It makes this structure for 2 reasons. It's going to want to put that lone pair of electrons as far away from the first pair of electrons as possible. They're going to be 180 degrees from each other, so as far away from each other as possible. And then the resulting atoms are all in a square plane. And I realize I'm kind of drawing this like a rectangle, but it's supposed to be a square. So if we look at it, there we go. We have our square planar. We have a central atom and then the 4 peripheral atoms, and they're all going to be 90 degrees from each other. What happens if we have multiple central atoms? So far we've only looked at one central atom. Multiple central atoms, basically a central atom is just an atom with 2 or more atoms around it. So anytime we have a structure that has more than one atom that has 2 or more atoms around it, we consider that to be a structure with multiple central atoms. And we're going to see this mostly with organic compounds. And with that, we almost always are going to max out at a tetrahedral geometry. So 4 electron domains. Right, so we won't go beyond that 4 electron domains for our multiple central atoms for the most part. Now, one of the things you guys should be able to do is to go from a structural formula, a condensed structural formula, to a molecule. So I'm going to do a couple of examples real quick. So from structural to Lewis structure. So we have something like CH3, CH2OH. These are going to be our central atoms. So we have a carbon connected to a carbon, connected to oxygen, and then we just place the hydrogens around it. Like so. Now, we don't have a complete Lewis structure yet because not everything has an octet. We're going to assume on these that they're going to all have an octet, so this structure would look like this, and this is ethanol. So we have 3 central atoms in this case. Each of them have tetrahedral electron domain geometries, but our 2 carbons have tetrahedral molecular geometries, while our oxygen has a bent molecular geometry. Okay, you can also see something like this, where you have CH3, 4C. So it's basically saying that all 4 of those CH3 units are around a central carbon. We have our central carbon and our 4 CH3 units. Like so. In this case, every one of our carbons is a central atom, and every one of them has a molecular geometry and electron domain geometry that is tetrahedral. Okay, we could also have something like this. So the hydrogens are going to be extra. Everything besides the hydrogens, those are the things that are kind of connected to each other. So we see that this oxygen that connected to this carbon, which is connected to this carbon, which is connected to this oxygen. So we do oxygen, carbon, carbon, oxygen, and then we put in our hydrogens. So it'll show hydrogen. This has 1 hydrogen next to that oxygen. This has 2 hydrogens next to that carbon, 2 hydrogens next to that carbon, 1 hydrogen next to that oxygen, and we get the structure. And again, then we will put in our lone pairs to give everything a octet. And all of our carbons have a tetrahedral electron domain geometry, molecular geometry. Our oxygen has a electron domain geometry that's tetrahedral, and then a molecular geometry that's bent. And then you can see something like this as well. CH3, C, parentheses, O, close parentheses, CH3. It could also be shown as CH3, C, O, CH3. Sometimes I'll write that on as test just to kind of clarify a little bit. And what this is showing with those parentheses is basically that oxygen is just on that carbon. So it's not part of the chain. It's off of the chain. And I put in this to show that it's double bonded. But usually this is going to be the form that you'll see. I only put this little equal sign to show that it's double bonded. So we have our carbon connected to our carbon, connected to this oxygen, but it's only connected to this carbon, and then that carbon. So it's carbon, carbon, oxygen, carbon. And then put in your hydrogens and fulfill octets by giving a double bond there, lone pairs there. So you should be able to go from structural formulas to Lewis structures, the condensed structural formula that we see here into your Lewis structure for a organic compound that's going to obey the octet rule. So these will all obey the octet rule. Okay, so let's try an example looking at bond angles for a long structure where we have several central atoms. So we're looking for anything that has 2 or more atoms surrounding it. So we're looking at this oxygen, this carbon, and this carbon. We need to take into account lone pairs and multiple bonds because both of them are going to cause more repulsion. So if we look at this oxygen right here, this oxygen has 4 electron domains and 2 non-bonding domains. So it's going to have a tetrahedral electron domain geometry and a bent molecular geometry. Okay, it's a tetrahedral structure with 2 lone pairs, so this bond angle right here is going to be 104.5 degrees. Okay, our 2 carbons, both of them have 3 electron domains, and they have 0 non-bonding domains. So our electron domain geometry and molecular geometry, both of them are going to be trigonal planar. Okay, so our electron domain geometry and molecular geometry are both going to be trigonal planar. Now, when we think this pair of electrons is going to repel more, so so any of the bonds that are around here are going to be greater than 120 degrees. And then the last bond is going to be less than 120 degrees. Okay, and that's it. At the end of the PowerPoint, at the end of this PowerPoint, you can look at a couple of different examples of each of the types of VSEPR structures that we have discussed today, if you wanted to look at some examples of some actual structures. But that is everything. I hope you guys have a great day, and I'll talk to you guys later. Bye.